Today we have Dr. Alex Godunov from the Department of Physics, and Alex is going to talk to us about problem solving, particularly as it relates to our students and instructing them or helping them to become problem solvers. So with no further ado, I'm going to hand straight over to Alex to say, tell us how we should do this, how we should train our students in problem solving.
Okay, thank you. Good afternoon, and first of all, I would like to say thank you for inviting me and coming here today. And the subject is quite important, not only for classrooms. So, problem solving. As Karl Popper said, and he was a British philosopher who was trying to develop theory of science, that all life is problem solving. Please do follow and ask yourself, since this morning, how many problems did you solve? How many problems you are going to solve today? How many more problems you are going to get on your plate just today? And what do you think about your ability to solve problems? Are you a good problem solver? And how did you learn that skill? And then how about your students? Are they good problem solvers? So let's see what experts think on this subject about human ability to solve problems. And a great expert, Daniel Kahneman, who got Nobel Prize, and he got Nobel Prize in economic sciences for psychology of human judgment, especially for taking decisions under uncertainty. But that's exactly what happens when we solve problems. We have uncertainty, and we solve problems under uncertainty. And his point is following that for many years, very many people believed that people are generally rational and their thinking, the problem solving, is good, normally sound. And the only problem when people have emotions, then they're maybe not so good. But with all the experiments now, it's clear that we can do systematic errors in our thinking. And we pay no attention. Even we don't know we do this kind of errors. So we're often confident when we are wrong. And let's share the opinion from a professor of behavioral economics from Duke University. And again, it's all based on experiments, not just some thinking, this is what I think. It's result of experimental psychology, now part of behavioral economics, that we are, in many cases, irrational. And we're irrational in the same way again and again. So it means we do same mistakes again and again, and we don't pay attention to that. And again, something for easy reading if you have time. Again, written by a professor of psychology with a subtitle, Why Smart People Do Dumb Things. I remember when I started reading that book, I thought, well, that's me. Oh, that's me again. Yeah, I do it. So a brief review. How do we solve problems? I'm not going to go through tiny details. It's kind of a general picture. How do we solve problems? And so we analyze facts, what we have. If we don't have some information, we're trying to figure out what to do with missing information and hoping it's going to solve problem. If it doesn't, we repeat it again. It's a very common and powerful approach, trial and error technique. And if it doesn't work, we just live with that, hoping for better luck some next time. And in psychology, they call that mental messing around, when we are not sure where to go and we are trying to find a solution. Most common things we do in problem solving. And if you read, this is exactly what we see in our classrooms. This is exactly what our students do. And we do the same also from time to time, maybe not so often, especially about thinking hard or discussing. It's a common comment from students. Or yesterday I spent 2 hours working hard on my homework. So what? But you didn't solve that. There's quite a difference, like going to a gym on a treadmill. You exercise, but you go nowhere. What affects our ability to solve problems? Yeah, sure, emotions. We know about that. No doubts about that. But there are mental shortcuts. And we need mental shortcuts because the world around us is so complicated that if we think all the time, we wouldn't go anywhere. But then we may get a problem when we see a new situation, and then what affects our problem solving, following patterns or biases. And again, quite often it's good. It's good. You are coming in a dark room and you are looking for a switch, and where to look for a switch, by the door, somewhere left, right. But again, for somebody who never was exposed to electricity, that somebody would have no idea where to look. And that somebody would keep his eyes open, but for us, we can miss something important that is different from a common situation. There was a nice article published in Scientific American right after this bubble and bust, with, again, home prices. And if we read that analysis, what we see, common problems, confirmation bias, overconfidence, then probably you would feel you see the same in your classrooms with your students. So your students are not much different from those guys on Wall Street. So it's the same problem. Well, in some cases, some students are trying to avoid solving problems, and I found that diagram on the web. And yeah, it's sad, but they follow that, trying to avoid solving problems, saying, well, if there is no solution, there is no problem. Let's talk a little bit about science and craft of problem solving. And here, very briefly, I want to mention just a few names, because it would take probably a whole day to talk about that history. Great minds in science were trying to solve solving problem. Right, like René Descartes. He was trying to find a general approach to solve any problem. Just you have any problem, you have one approach, would solve everything. And he didn't succeed because it's too complicated. Just one more name I want to mention in the end, Karl Popper. He's quite famous in the philosophy of science, and he put considerable efforts to develop theory of science, actually problem solving. So if you open his writing, you may find good history about problem solving. I'm going to talk about just one book specifically. That book was published in 1945 by a mathematician. His name is George Pola. And his intention was to find a way to help students, especially students, to solve problems in mathematics. And his approach has only 4 phases, or we may say 4 steps. They're quite obvious. Number 1, to understand the problem. Number 2, to create a plan. Number 3, just follow your plan, and eventually you look back. Let's go very quickly over this approach and to see what is easy to implement and what is challenging. Well, understanding the problem. Yeah, it's quite obvious. How can you solve a problem if you don't know your problem? And by the way, talking to students when they are coming to me during office hours or in physics learning center, when they have a question about some problem, I'm telling them, no, I'm not going to read your textbook or from a screen what is there on Mastering Physics. Tell me, what is your problem? And quite often, they can't even tell me about their problem. They don't understand the problem. And I like that quote from Einstein, that you don't really understand something unless you can explain it to your grandmother. It's a good approach. You want to understand your problem, imagine that you are talking to your grandmother or somebody of your relatives who are not expert in this area. You would understand your problem much, much better. So with the first part, it's clear. It's more or less understandable. The second part, creating a plan, looks like complicated, and it's stated it's complicated. You are supposed to have good knowledge, because if you don't have knowledge about that subject, how can you solve a problem? But then besides, you need good mental habits. You need good concentration on the purpose. So it's kind of a guideline. It's not a roadmap. But at the same time, sure, we need to start here solving the problem. Then the next step, carrying out a plan. And it's more or less understandable. You have a plan, stick to it. Don't jump back and forth be sure that your plan, for example, doesn't work. Then you come back to the second phase and you're trying to find a solution again. So it's quite easy. And then the last one that is obvious for many of us, not for students, look back. Why is that? For many students, their ultimate goal, especially in math and physics classes, just to get a number. They have a number, they type that number, web assigned, master in physics, and they're going to live happily ever after. But it doesn't happen, because quite often they're getting, oh, that's wrong. But if they were lucky or a miracle occurred, and that number was accepted, they don't look back. They don't estimate what was true, what was wrong. And I'm going to talk a little bit more with some examples from physics classes. So, looks like a good plan. But at the same time, just mention a little bit about craft, not only science. There are so very many books on the market about problem solving. Many of those books not actually about theory of problem solving. It's craft, how to solve specific problems in some specific areas. For example, in some specific areas of engineering, or some specific problems for military. Yeah, it's still good, but their problems very specific. And many of those methods are so specific that it's difficult to implement in science classes or when you teach. Nevertheless, you can find something useful even in those books. For example, out of those specific techniques, Devil Advocate, it's one of my favorites. You have an idea, you're coming to your colleague, and your colleague plays like a devil advocate, and then before submitting your paper, you're sure, yes, I need to work more. How about popular culture? What are good examples for our students? And when I polled students in my classes, Dr. House was #1 as a great example for problem solving. So we need to keep it in mind. What do our students know or they believe is a good example for problem solving? And it's not a bad example. So that's about theory. We have a good plan, 4 steps for problem solving from George Poller. We have some craft, books, ideas. What happens in classrooms? Not generally, in physics classrooms. And it's a common complaint from students that, yes, I do understand the subject, I just can't solve problems. Despite there's quite a good progress in teaching physics. There's peer review, collaborative learning, and we implemented scale-up. It all helps to improve their understanding, but then there's still a problem with problem solving. So why that? Why students most often are trying just to plug and check? Well, there are some habits they pick up from schools. And then we need to deal with bad habits. And we know it's difficult to change bad habits. Let's have a quick look on an example from a textbook. It's a very good textbook. We use a textbook. It's an example how to solve problems, let's say, on conservation of energy. The example follows George Poller's idea, 4 steps. Initially, yes, identify, it means understand your problem. Then set up or create a solution or a way to solve the problem. And then again, execute, implement, and evaluate, look back. Looks like a good plan, but at the same time, you talk to students who use those textbooks. They're coming to you saying, well, I understand all those specific examples, I just can't apply that to solve homework problems. So what is the problem there? And I believe the answer to this problem is in step 2, creating a plan. Because it's too general. Students are not good enough. They are not experts like us. They don't have much experience to develop a plan. And that's the reason that they don't know what to do. On the second step, they hope for a miracle, type in some answer into master in physics or web assign, and because they don't know anything else what to do. Well, we may say, that textbook may be too general. We need to be a bit more specific. Well, there are examples to be more specific. Another example from a textbook. For every chapter, they have specific set of recipes what to do, how to solve a problem from a specific chapter. And this is not a bad textbook. I know some other examples where you can find for every chapter like 12 steps for solving problems inside that chapter. Well, if we multiply that on average we cover 12 to 20 chapters in a semester, then it means that somebody expects students to remember 100 steps how to solve problems. And then on final exams, I always give problems that are combinations of problems from various chapters. And then it wouldn't help. Why it doesn't work? Because textbooks are not supposed to be cookbooks. Yes, when we cook, we don't ask questions. Yeah, there are some great chefs, and we learn from them. We just follow their examples. We don't question why to do that. But if we have a textbook, like a cookbook, then everything is quickly forgotten. Then students don't understand why doing that, and if somebody has good memory, it may help to survive. And not good memory, then they're trying again to find some easier ways to cheat or solve. So it's clear that both approaches are not great. Recently, there was a paper published with a title, "Are Most People Too Dumb for Physics?" Why that? Because some professors, not our colleagues, they believe there is no point to teach physics at all. Why? Because physics is too difficult for an average mind. Then the physics has no relevance. Then later students would graduate, they would go to engineering or history, they wouldn't need physics. And then conceptual physics is way too shallow. And 3 professors, including Eric Mazur from Harvard, they care about teaching. They wrote a paper, they disagreed completely with the statement. And from that paper, I want to bring one quote. From their point of view, one of the basic learning outcomes of a physics course is the ability to solve problems. Yeah, this is the most students would learn from our physics classes, and I believe from math classes and other classes. Because they may forget something specific, but how to solve problems, how to think, they would take with them forever. And then imagine if you are visiting a doctor, and that doctor, well, maybe remembering something specific, but isn't a good problem solver. Then you would feel you can be in trouble. The same for teachers everywhere. So we want people we communicate to be good problem solvers. And then we want our students to be good solver problems. It's our responsibility. Well, let's see what do students do. And my son sent this cartoon, and yeah, it looks like it's pretty much true. And when you are done with the first slide, I'll show you the second slide. Can I go to the second? Well, besides, that's not the only problem we face. The other problem is, yes, social networking. And some people believe that the more people communicate, let's say on Facebook, then they're getting smarter. They're sharing some ideas, beliefs, understanding, and they're getting smarter. Well, sadly, people in psychology doing research, they demonstrate, no, it's quite opposite. But then the problem with each class, and you see what very many students are trying to do during their class. They go to Facebook to post something new, like I'm sitting in that boring, stupid class, and they believe that whole world would say, oh, I feel sorry for you. Like, well. So let's see what can be done. When we have a problem, what would be the best way to do if you don't know what to do? Go around and ask people who may have a solution or who may have an idea to help you. Because what happens with our thinking, we believe that we are getting ideas, great ideas, when we have all good ideas, just from nowhere. No, like 95% of our great ideas are coming when there is a collision with ideas from other people. So we need to talk to other people, or at least to know what happens across a field. And I was lucky bumping into that book written by Nobel Prize winner, as I mentioned to you, Daniel Kahneman. And it's written for psychology majors, for people in business, but reading that, I saw explanations to what I saw in my classes. And then I asked myself, would it be possible to apply anything from over there to improve problem solving in our classes? And the idea is following, that we have like two systems in our brain, in our mind. The first one, it's mostly autopilot. This is the way we navigate. We drive empty road. We don't think about driving. We're on autopilot. And we do many things on autopilot, because that system is very good to generate quick solutions, not for real problems. Looking for a pattern, yeah, this is what I did, it's going to work. But then when we have a problem, what happens? For us, professors, when we teach some subject for years, and if there is a problem, we go through the left line, what is called expert solution. Spontaneously, immediately, we see an expert solution. We know how to solve that problem, even without thinking about that. Why? There is no mystery behind expert solution. It's just a result of practicing. And people, again, playing music, they know you want to be a master, you are supposed to practice a lot. And we practice it so much, we just do that automatically. But our students, they're on the right side. They are not experts yet. So, and then they are trying to do what is called intuitive heuristics. And they have very many biases. And many biases are common for very many people. And if we understand biases for our students, then we may address the problem better. And then the second type of thinking, what is called slow thinking, or system 2 in psychology, it's slow, it takes a lot of mental energy and effort, but actually this is where we solve problems. When our first system isn't able to generate solutions, then normally we go to the second system. And that system, yes, we may control our thoughts, and that system is very powerful, but then it takes a lot of energy. The problem in physics classes, and I believe probably in other classes, the students going through the right side, this intuitive heuristic, they pick up some solution, and that solution is wrong, could be wrong. And I learned recently that to know that you are wrong, you are supposed to be good enough to know that you are wrong. But they are not good yet. And they stop there, they don't go into this slow thinking mode. So we need to find a way to help them with their intuitive thinking and push them to use their system 2 or slow thinking. A couple comments, again, from the book about intuitive heuristic. That when we are faced with difficult questions, especially under time pressure, what happens? Quite often we substitute the original question on easier question. And then I thought, well, now I understand, because in many cases I saw the students doing midterms or final exams solved some different problems, not problems I gave to them. And I thought, well, probably they wanted to pick up some extra points. No, it happens. They just don't see they're solving a different problem. And in the book of Kahneman, there's an example. Let's say there's a stockbroker who needs to solve a problem, whether to invest into, let's say, Ford Motor Company. And it could be a difficult question to evaluate the market, and under time pressure, a boss is coming and you need to produce answer within 5 minutes, that somebody may substitute the original difficult question into an easier one. Do I like Ford cars? Oh yeah, I like. Okay, let's invest. This is what students do. So we need to find a way to prevent them from this jump. The other example, availability heuristics. And what people remember, what is easier to retrieve from memory, then they believe it has more value. And it also explained to me what I saw in my classes. I saw that some students were trying to solve all problems on, let's say, some midterm using just one equation. Because it was just one equation, they remember it. And that was only one available to them. So we need to find a way there's more in their memory. Yes, and a problem, yes, students try to consider any problem isolated from anything else. And I'm not joking, you give them a problem, let's say, about a cat jumping from a roof, and then 2 days later it could be another problem, and another problem it could be, let's say, an elephant. And for students, some students, there are going to be two different problems. Like a cat problem, like you need cat equations in physics, and then an elephant problem, like you need elephant equations in physics. They don't see it's the same. For us, it's obvious. For them, it's not so obvious. About slow thinking, yes, system 2 is the only one that actually solves problems. But at the same time, that system needs concentration and attention. And our attention budget is limited. So when we do something else, it means we have less attention for system 2. And this is what happens with students. They think about Facebook, and it means less attention for actually solving the problem. And then the other, intensive focusing on one task can make people effectively blind. We can be blind to the obvious, and we're also blind to our blindness. It's not so much for students, I believe it's for us. When we're so much involved into something, we may not see something else. And it's normal, you know, there is nothing wrong with us. That's the way our memory operates, our brain operates. The other, reading a book written by a psychology professor from Scotland, I believe, I bumped into an idea that thinking and writing, there are two different activities for our brain. And then I thought, wow, what we do at ODU, placing so much attention on writing, is actually great. Because when we think, we normally think spontaneously. We jump from one place to another. But when we write, we need to create a story. We need to think logically. It means we engage our system too. That's what we need to do in our science classes. We want students to engage the system too, and through writing. So writing not only in history classes or literature, well, in science classes too. A few ideas. They're variable quotes from great people. And if you think how to use that in classes, you may find out, yeah, it's valuable. But I only want to discuss the last one. And you may say, well, I don't see any connection to problem solving with the last quote. That laziness is built deeply into our nature. Yes, because again, if there are several ways to achieve the same goal, we're always trying to find the easiest way. It's like less action in physics. It's the same. Why it's relevant to problem solving? Speaking about our students. Let's say a student has a homework problem or a homework assignment that is due in 1 hour. And they may substitute the original question to solve their homework assignment onto another question, how to get most points from my homework assignment. And then their thinking goes, well, to do that with less possible efforts. And they do that going to Google. So actually they cheat. You go to Google and you find solutions to most problems on mastering physics with web design, and they don't learn anything in this. So we need to find a way to close the door for them. That easy door, you go to the web and you pick up solutions, you plug in numbers in mastering physics, and you are happy or hoping to get so many points. So as a result, what do? On the department, we take teaching very seriously. We believe it's extremely important. Yes, we're involved in science and physics, but we take teaching very seriously. And About 2 years ago, there was an experiment in my class. It was in physics 231, and later I started using that in other 231 classes, also 111. 231 is introductory physics calculus based, 111 algebra based, and communicating with my colleagues, so we implement more and more of this approach. So what is the idea? I don't have much time to go through every point saying how to connect that point to ideas in the book published by Daniel Kahneman. So I'm going just to tell you what do we do. So we enforce students to follow these 6 steps. They are general steps. They are not specific for some specific chapter. They are general steps. It's kind of a refinement, ideas from polar, but keeping in mind of psychology, how do we solve problems. And number 1 is following, name and write down, write it down, the type of physics most likely related to the problem. So we want students to write down, to engage their system 2, slow thinking, what is there. And after that, the next step, write down most basic equations for this chapter, or for this physics. On if student believes there is more than one physics, okay, write down more. What happens in this case? In this case, instead of trying to guess a solution, it's like being a police detective. You place all your suspects in one room. And then your problem is easier. You know, somebody who did it sitting in this very room. It's much easier than going around trying to guess where it could be. Then the next step, simplify these basic equations as much as possible. And do that in symbols. Because very many problems, they're easier than basic equations. And when students do that, they see a way to actually solve them. After that, when they have this, we may say, adjusted equations, solve them again using algebra, using calculus, no numbers. Because I believe when somebody sees numbers, then physics is lost. So you need to think with symbols, like happens in nature. And then when you have a solution in symbols, plug in numbers, and the last very important step, maybe the most important, evaluate your answer using common sense. Yes, in physics it's possible to do that. Use your common sense. Also, we enforce assignment journals. Because again, students do their homework. When you teach a class, 100 students, it's not possible to grade their homework assignments. Every week, about 10 problems, 100 students, 1,000 problems to grade. It would take whole week. Yeah, years ago, professors had TAs. Now we use WebAssign and Master in Physics. The way it works is following. Student opens, let's say, a page in Master in Physics, sees the problem, solves, hopefully, and then types in numbers. And then back, there's a reaction. Yes, accepted, green, or not accepted. Try 3 more times. So the way they solve the problems, piece of paper to the best, and their thinking is not organized. So we want them to have assignment journals. Whatever they do on Master in Physics, they're supposed to solve first everything in their homework journals. And then those journals are collected once a week, not to grade, no, just to check that they use their homework journals. And what do I do in my classes? I do following. I instruct the TAs to grade their journals in the following way. If there is nothing for that homework, then 0 coefficient. And doesn't matter, whatever they have on Master in Physics is multiplied by 0. So they have no credit on Master in Physics for that. Then, if there was some, let's say, mumbo jumbo, okay, 0.5, at least something they tried to write down, anything. But if they followed the rules, then they have full credit. It's an example, quite a simple problem. The way we want our students to solve problems. Yes, to write down what physics, and that was about some cat jumping from a window, and to write down most general equations. And what is interesting is following. For example, for that chapter, all solutions to all problems are inside those 4 equations. They're the only students need to solve any problem in the chapter, no guessing. It's like they have their suspects in one room. It's all there. The question is how to get your answer out of there. And then we provide with a guideline, not guessing. Just go there and it's going to be there. And then eventually they are supposed to get that answer. And speaking about those answers, yes, if students don't use that approach, they flip pages in their textbooks trying to look find an equation with something like x, range, or time of flight, and they may find wrong equation, and they may plug in numbers into wrong equation. And by the way, this problem was given on some midterm exam some time ago in my class. And some students, they didn't do the last step to check their solution using their common sense. And the longest distance was about 2,000 miles. So can you imagine a cat jumping from here, from Norfolk up to Canada? The longest time of flight was about half an hour, kind of flying cat. And then I asked students, have you ever seen a cat? And the answer was yes. And I said, well, it's the same cat. And the answer was, no, it was just physics. So you see, there's a gap between science and reality and what we have in students' minds. They believe physics is just physics. It has no connection to reality. So what is the key feature what we implement? Basically, what we're trying to do is following. We're trying to help students to develop expert thinking. That's what we're trying to do. We want them to think like us, not to memorize some patterns for solving some specific problems. All those patterns are going to be quickly forgotten in 1 semester or 2 semesters. So that is the key idea, and we do that addressing following issues, trying to help them here. It means with their intuitive thinking to reduce number of biases they already have after school, and then pushing them hard to go into this slow thinking mode, what is called System 2. Just on that diagram, this 4-step problem-solving approach, we expand a little bit this second step. And yes, we made it a bit more specific for physics. And if you're in chemistry, biology, you may need to replace this number 2 to expand differently. But this is what we did. Not much from one point of view. At the same time, it works. And it works much better than, I would say, I was more critical initially than we expected. First of all, we did an experiment approved by IRB. In a class, we had a couple groups. One group was doing like most students do before, just mastering physics, whatever you do, it's fine. And the other group was enforced to have homework journals and to follow the rules. And what we saw at the end on the final exam, and the final exam was only problems. So by about 25%, this second group did better. And what surprised me even more, every semester, we are trying to understand how good we are or not good we are teaching students. So we give the same quiz at the very first week and at the very last week. And then we compare how much actually students picked up from some class. So we use what is called forced concept inventory test. And students who were following this set of rules, how to think properly, they improved their performance by 42%. It's quite a jump. And then after that, I implemented that in all my classes I teach. And I see constantly, yes, there is a great improvement. But at the same time, speaking about those averages, like 24, 42, we need to be careful. Because average could be deceptive. Like, let's say, average temperature in a hospital. It could be normal, but at the same time, we have 5 people with high fever, with flu, and 1 is already dead. And the average is OK. So what happens is following. Many more students are now getting A's and B's. But speaking about F's and D's, the impact is much less. So to address the problem, we need to find probably some other solutions. But again, it helps enormously good students. And let's see what students say. And I pick up some, again, their comments after the class. And practically in every comment, you may find that word thinking. And I said, wow, that's good. So we teach not only physics, we teach them how to think. And again, even more on the other page. Some concluding remarks, because I'm trying to stay on time, as I was told. And my remarks are following. OK, so we have something that works in our physics classes, at least in some physics classes. We're trying to propagate more and more. How about other classes? And generally, how about us? Can we do better in solving problems? But there's a question, actually a couple questions on my mind, I don't have an answer. What is that problem solving? Is it science or art? And if it was science, why don't we have, again, departments like problem-solving departments on our College of Science or anywhere? I check the Google, no departments. Well, some people are saying, no, problem-solving is mostly art. It's art. It's just art. Then we should have on our College of Arts and any other university, not only, again, Department of Music, Department of Problem-Solving. And then usually they do nice performances, like in music. Why don't we have performances from people who are great artists in problem-solving? So it's clear, it's quite a complicated subject. It's so important for our lives. But it's science and art and craft, and we master that going through our lives, because generally there is no silver bullet saying, yeah, that's a solution to every problem. But at the same time, what we may conclude, at least my humble conclusion is following. When we want to teach somebody to something, we need to know how do they think. And if we want to teach problem solving, we need to know how do actually people solve problems. And we may get great help across the board. Yes, we want to teach physics, but in psychology and business, they also learn a lot. Even in this strange sounding, like behavioral economics. Yeah, you may apply so much from their knowledge. And it's multidisciplinary. So we need to talk to each other also, I believe, inside the university. And this kind of meetings, provost conversations. And yeah, we just need to leave our offices and to talk to each other. We have a problem, maybe somebody else has ideas. Not a solution, but ideas to help us. And then speaking about solving problems, there are specific measures, but at the same time, there are quite fundamental steps. And when we teach, we need to remember going from fundamental to specific. If we are too specific, if we believe that our students are not good enough, let's teach them an easier way, like let's say that our planet is flat, otherwise they could be confused that it's round, why people in Australia don't again fall down. No, we need to take it seriously and to teach them like it is, not to be too simple. And at the end, at the same time, I just want to tell you that in some cases, the easiest way to solve problems is this one. Yeah, thank you.